the product p of x times q of x is given by a0 x to the 0 plus a1 x to the 1 plus a2 x to the 2 all the way up to an x to the n times b0 x to the 0 plus b1 x to the 1 plus b2 x to the 2 all the way up to bn times x to the n. Now to multiply out these two polynomials, we multiply out each term in the first factor with each term in the second factor, and then we group together like powers. So how can we get a power of x to the 0? Well, we can multiply a0 x to the 0 with b0 x to the 0 to give us a0 b0 x to the 0 plus 0, and that's our only term. How can we get a power of x to the 1? Well, we could do a0 times x to the 0 times b1 x to the 1, which gives us the term a0 b1 x to the 0 plus 1. We can also have a1 x to the 1 times b0 x to the 0. So this gives us a1 b0 x to the 1 plus 0. Thus our coefficients c0 is equal to a0 b0. c1 is equal to a0 b1 plus a1 b0. Now how can we get a power of x squared? Well, we could have a0 b2 x to the 0 plus 2, which is this term multiplied by this term. We can also have the product of two linear terms, so this term times this term. So that would be a1 b1 x to the 1 plus 1. We can also have the quadratic term times the constant term, which gives us a2 b0 x to the 2 plus 0. Thus c2 is equal to a0 b2 plus a1 b1 plus a2 b0. Hopefully you've started to notice a pattern here. This sum of the indices are equal to the index of the coefficient that we're trying to find. Thus, continuing this pattern, we would get that C3 is equal to A0 B3 plus A1 B2 plus A2 B1 plus A3 B0. So how far can we continue this process? The A's increase from 0 all the way up to AN. And similarly, the B's can only decrease from BN to 0. So we can continue this process until CN, where we get A0 BN plus A1 BN minus 1 all the way up to AN B0. However, we have 2 times n of these coefficients, so we also have C of n plus 1. So how can we make a coefficient of n plus 1? Well, now we can't start at A0 anymore. We need to start at A1 times b to the n plus A2 times b to the n minus 1 plus A3 times b to the n minus 2 all the way up to AN b to the 1. And we continue this process until C sub 2n, which is equal to A sub n, B sub n. More generally, we can write down the formula for I between 0 and n. We have that Ci is equal to the sum from j equals 0 to I of aj times b I minus j. Now for I between n and 2n, we have that Ci is equal to the sum from j equals I minus n to n of aj times b sub I minus j. From the previous part, we have that for I between 0 and n, Ci is equal to the sum from j equals 0 to I of aj times b I minus j. And for I between n and 2n, we have that Ci is equal to the sum from j equals I minus n to n of aj times b I minus j. So for this sum here, we have the sum of I plus 1 terms. Each term consists of one multiplication. So we have I plus 1 multiplications. And summing up I plus 1 terms requires I additions. For I between n and 2n, we have the sum between n minus I minus n plus 1 terms. This is equal to 2n minus I plus 1 multiplications. Summing up 2n minus I plus 1 terms requires 2n minus I additions. To calculate the total number of multiplications, we sum over the number of multiplications it takes to calculate each of the CIs. So the first sum is going to be from I equals 0 to n of I plus 1 plus the sum from I equals n plus 1 to 2n of 2n minus I plus 1. This first sum here will be the sum 0 plus 1, which is 1. The second term is going to be 1 plus the first term, so it's going to be 2, all the way up to the final term where we plug in n for I, so we get n plus 1. So we see that this first sum is just the sum of the first n plus 1 integers, which is given by the formula n plus 1 times n plus 2 over 2. Let's do the same thing for the second sum. Plugging in n plus 1 for the first I gives us 2n minus n plus 1 plus 1, which is equal to n plus 1 minus 1, leaving us with just n. The second term is going to be 1 minus the first term. So the second term is going to be n minus 1. And then the next term is n minus 2, all the way down to the last term, which is 2n minus 2n plus 1, which is just 1. So we see that the second sum is just the sum of the first n integers in reverse, but the sum is just the same. So the sum is n times n plus 1 all over 2. So in total, it takes n plus 1 times n plus 2 over 2 plus n times n plus 1 over 2 multiplications. Now let's do the same thing for additions. The total number of additions is going to be the sum from I equals 0 to n of I plus the sum from I equals n plus 1 to 2n of 2n minus I. So this first sum here is just the sum of the first n integers, which is given by n times n plus 1 over 2 again. Now let's write out the second sum. The first term of the sum is going to be 2n minus n plus 1, which is just equal to n minus 1. The second term is going to be 1 minus the first term, so it will be n minus 2, all the way down to the final term, which is 2n minus 2n, which is 0. So as you can see, this is the sum of the first n minus 1 integers, which is given by n minus 1 times n over 2. So the total number of additions it takes is n times n plus 1 over 2 plus n minus 1 times n over 2. The formula for p of x is given by the sum from I equals 0 to n of ai x to the I. Writing out this sum more explicitly, we have that it's equal to a0 plus a1 x to the 1 plus a2 x to the 2 all the way up to an x to the n. Now let's compute how many multiplications it takes to compute x to the I, where I is greater than or equal to 1. X to the I is just the product of I terms so therefore it takes I minus 1 multiplications. Thus x to the 1 takes 1 minus 1, which is 0 multiplications. X squared takes 1 multiplication, and xn takes n minus 1 multiplication. But we also have to multiply x to the I by ai. So in total for each term we need I minus 1 plus 1 multiplications for each term. Notice how we don't need any multiplications for the first term because it's just a0. So the total number of multiplications is going to be the sum from I equals 1 to n of I minus 1 plus 1, which is just n times n plus 1 over 2. Now let's count the number of additions. The number of terms in this sum is n plus 1. So therefore, we only need n additions.